All right. So among the areas you suggested that we cover, the most outstanding from across most of the classes was current electricity and also waves too. So we shall try and go through current electricity, if possible, the whole of it, and especially the key areas. And then maybe in our next lesson, we can now check on waves too. I think by that we shall have bridged some gaps that are there in paper 2. Current electricity is a paper 2 and also very important for paper 3. So those concepts are also tested in your practicals, the concepts of current electricity too. So without much further ado, some of the objectives you're supposed to try and achieve, you're supposed to, at the end of the lesson, you should try and know the definition of what electric current is and maybe the potential difference. We shall check on the measurement of electric current and maybe potential difference. We shall try to understand also the connections of components, both in series and in parallel. After that, giving that introductory, we shall check on Ohm's law, and we shall check at the definition, the graph, and maybe go ahead and mention ohmic and non-ohmic conductors. From there, we shall introduce a concept of electrical resistance, factors affecting the electrical resistance, and maybe the formula and some few examples of problems that involve using that formula. From there, we shall mention resistors, define and give you the different types of resistors briefly. Then we shall go to the core of the topic, that is resistor networks. From there, maybe if we still have time, we shall finish with the idea of the internal resistance and the EMF of a cell. So that is a rough overview of what we are supposed to go through. So, and we have at least around less than 2 hours to finish on that. So we shall move first on especially theoretical parts and give more emphasis especially on resistor networks. Because that is actually the main thing in this topic, and that's where most of us have problems in. If I remember, one of the questions in our end of term, paper 2, was on resistor network, and it was having around 7 marks. I think a majority of you could not get that question because of the issue of the internal resistance of the cell that was introduced in that question. So that's where our core is supposed to be, and we shall take some ample time to understand that area. So allow me begin with the definition. Before definition, our topic is current electricity 2. And this follows current electricity 1 that we did in Form 1, what we normally call cells and simple circuits. It introduces us to the concept of electricity, but at that point, we tend to look at what we call static electricity, like the one that charges are being built up on a surface, but they're not living or they're not moving by. They're just being built up and they're not moving. The charges are not moving, hence static electricity. Now here we are bringing the idea of current electricity, means that the charges are now allowed to move. That's where the idea of current electricity comes in. The charges are able to move through. So that's what we are interested in. And of course, this is one of the main things we do apply. Of course, we apply current electricity. So many devices use electricity, like for instance, the phone you're using, the laptop you're using, the radio, the televisions, the electric cooker, we have the iron box. There's so many things that uses electricity. And that's why it is very important for us to develop a solid understanding of current electricity. Apart from that, the main aim of, the major thing in the topic will be resistors. And of course, resistors are devices that are present in so many electrical circuits. We have them there. They're always present in radios, everywhere. They are always existing, and they have a very serious role to play. That's why it is important to understand what resistors are, how they're made up, and how we can always arrange them in any circuit. So beginning with the definition of the first term, what you call electric current. So electric current comes in when we have a charge. Of course, there must be charge. Whatever is responsible for electrical conductivity are always electrons, which we basically call them charges. So we'll have a charge, which is an electron. And if this charge is able to move from one point to another through a conductor, this point A, this point B, and this electron is able to move through with time, then it brings the concept of current. So current is simply defined as the rate of flow of charges from one point to another in a conductor. So this may be our conductor with the length A to B, and I have some charges, that is electron, and they're able to move, of course, with the time. Then they bring in the idea of current. So mathematically, or maybe in an equation form, we say that current is simply given as the charge divided by the time. So you can define it as the rate of flow of charges, or you can define it as the amount of charges flowing per unit time. So that is the formula for the current, and that is bring the idea of the definition we have just stated. So in expressions, I mean in symbols, current is normally denoted by the letter I, and then the charge normally denoted by the letter capital Q, and then time is small t. So you can even have this your triangle there as Q is equal to IT. So this one you should know, you should have it at your fingertips, so that you can always solve any problem that is involving charges, current, and time. The SI units are important for anything we mention in physics. These are quantity, of course, and is a scalar quantity. Current is a scalar quantity. Charge is also a scalar quantity, and time is also a scalar quantity. So the SI units are also very important. For charge is always in coulombs, capital C, coulomb. Time is always in seconds, small second, of course, small letter S, that is second. Then the current, of course, we normally give the definition to be, the SI unit is to be in ampere, capital A, ampere. And this is because of the scientist, the ampere, who help us in so many areas in electricity. But 1 ampere is dimensionally equal to 1 coulomb per second. So all these units can be used. You can stock of ampere, or you can use of 1 of coulomb per second, though the most preferred one, of course, is amperes, unless you want to see how the units disintegrate and they get used into some more complex equations. That's why it is important to bring in now the dimensional ones, these ones here, so that you see how they solve. So, there's a question already? Any question? All right. Sorry, I'm not able to read the messages in the chat box. So if you have any question, just unmute and you can ask it. If you raise your hand, I may not easily see. So maybe you are allowed to interrupt, and you interrupt for constructive reasons, not for destructive reasons. So you are allowed to interrupt and ask any question, or if something is not clear, you can always say. All right, so that is the idea of electric current. So that is important. We know that definition, the formula, how it relates it, and also this SI unit. I've said it's a scalar quantity. Yeah. In a short while, I'll talk about how it is being measured. So is that okay?
Yes.
Yes.
I don't want to give an example on this, because this one you have been seeing since Form 1. So I'll give an example in the next definition. So that's just a definition of electric current. Allow me to talk about the next definition thing I want us to define is what we call potential difference. And make sure you write something. You have somewhere you're writing some short notes and solving problems that I'll be giving. It's not a show. I just watch. So make sure you have somewhere you are writing. You have a calculator and every detail. You are fully set. So potential difference. in short form, we normally just write as PD, potential difference. So again, back in our current electricity one, we define these terms of potential difference, and we also defined EMF. And those definitions were rather shallow or were rather simple. In Form 1, we simply allow definitions like potential difference. We simply allow it to be the voltage, voltage in an open circuit. I mean, in a closed circuit, voltage in a closed circuit to be PD, while voltage in an open circuit to be EMF. But now when we go to the details of this, we expect the definition to be in terms of work done. Let's check. Suppose this is a conductor. This is a conductor again, and we have this conductor point A and point B. And suppose you have a charge. For a current to be there must be charge that is flowing through a conductor. For instance, you have a wire. You have been in the lab, so you have those wires. Anytime you connect the wire, of course, through the terminals, then the electrons are supposed to be flowing there. So as the electrons flow, they bring the ideal current. Now, for that electron to flow, so suppose you have a charge here, that electron here, it needs to move from this point A to point B across that. So we expect that work has to be done. For us to move this charge from point A to point B, we have to do some work. And that work done in moving a unit charge is the issue of the potential difference. That's the definition of potential difference. And of course, energy will be supplied, and the energy will be given by a source of EMF. And that source can be a dry cell. For instance, in the lab, in your practicals, you'll have a simple circuit, for instance, that the symbol of maybe a dry cell. Then if you like, you can have a switch there. Then maybe you have a bulb there. And your circuit, suppose, is complete that way. So this side is positive. The longer, where we are having the longer sign, is always positive. The shorter one is always the negative one. So ideally, whatever is true is that the charges, of course, will be flowing. The electrons will be flowing in this direction. The charges will be flowing in this direction, from negative all the way to the positive. That will be the electrons flowing in that direction. So, of course, work has to be done, of course, in moving it through that conductor. And of course, that is the direction of the charges, that is of the electrons. But normally, we use the conventional direction, which is always from the positive to the negative. So we say that current is flowing from positive to negative, but actually the electrons which are responsible for that current normally flows in the opposite direction. So that is what we have. So when this part is closed there, of course, work has to be done in moving these charges, of course, and that energy to do that work be supplied by this dry cell that is there. The dry cell, or maybe a battery, will always give us that energy, and like that. So in defining potential difference, we talk of PD to be the work done. So if you are to have a voltmeter, I'll talk about it later on to place it there. The PD is defined as the work done in moving a unit charge from one point to another in a conductor. Maybe you can write that definition if you're interested. So it's the idea of the work done in moving a unit charge from one point to another in a conductor. So that's the issue of the potential difference, and we normally measure is in volts, or in volts. So the symbol also just V. So V is more of work done. Work done in moving a unit charge, like that. Of course, our charges here are electrons. That's the idea. So I can maybe give a simple example to illustrate that idea. So an example is here. That a circuit is supplied a circuit is applied it's applied with 3.0 volts. Determine the work done. Determine the work done in moving 20,000 electrons in the circuit. So you can have that a circuit is applied with the 3.0 volts. Determine the work done moving 20,000 electrons in the circuit. Be trying that. So let's solve it. I think you're done. Let's see what we have. So in our solution, whatever we are given there, we have the potential difference, or V, is given as 3 volts. And then the charges involved, Q, or the charges involved, is 20,000 electrons. So we have our definition as the potential difference V is simply the work done in moving the charges Q. So from here, you can see that the work done is supposed to be given as the number of electrons involved, that is the number of electrons here, times the voltage. So it is mod of Q times V. So it will be the 20,000 times 3 volts. And then we'll get 60,000. What is the SI unit of work? What is the SI unit of work done?
Joules.
Joules.
Joules. So in the future, we shall generalize this formula. This formula, we will generalize it later on in future. But for now, let's just take it simply like that, the way we have done it that way. So that's just a small to illustrate the idea of work done in moving a unit charge through a conductor. So that is what we define as the potential difference. So I want to take much time on that. I want to go to measurement of this electric current and potential difference. The measurement. So measurement of electric current. So for current, we measure with the device. The device is called an ammeter. Ammeter is the device used for measuring the current in a circuit. And of course, the ammeter is supposed to be connected in
Series.
In series. Very good. Why do we connect ammeter in series?
To offers less resistance.
Yes?
It offers less resistance.
Yeah, very good. Very true. Ammeter is a device of very low resistance. So if you do a mistake of connecting it in parallel, of course, the end result that it will short circuit the other loads, whatever else you have connected there. How do we connect that in diagrammatically? So if this is a source of the PD and maybe a switch is there, so you're supposed to have your ammeter maybe there, like that. Then from there, you can have your load. It can be a bulb, that way. So in that case, you are able to measure the amount of current that is flowing through, that is passing through that bulb. So this will be our ammeter. There's a symbol for ammeter. You circled an A to mean the ammeter. Of course, this is a switch, and of course the dry cell is there. So the direction of the current will be like that, from positive to negative, like that. So something else to take note of, the ammeter, also you have to ensure that you connect positive to positive, then negative to negative, so that it enters through the positive, then leaves through the negative, like that. So that is a very important as you connect the ammeter. And then don't connect it in parallel, because if you do the parallel connection looks like this. You have it, that is your cell, like that. Then suppose this is a bulb, the main load in the circuit, then you come and place it here. You place the ammeter there. You know, normally current prefers a path with very less resistance, very less opposition. So when the current will be flowing, it at this point, it meets a junction. So when you get the junction, then this route will have very less resistance compared to this route. So most of the current, almost all, most of the current, not all, take note of that, not all, most of them, a good number of them, will tend to flow through, most current will tend to flow through the ammeter, like that, and bypass this, our bulb. And yet our bulb is our main interest here. So in that, in the end result, the bulb may not give you any light, or may be too dim, or may not even give you light at all. So in that case, you say that the bulb has been short-circuited because of the ammeter. So ammeter is a device of very low resistance, so you should not connect it in parallel to any other component. It should be connected in series, as in this diagram here. And of course, as you use that ammeter, make sure that you pick the appropriate scale. And in that appropriate scale, ensure that you know how to use that particular scale. You simply need to know that what is the amount of current you expect. If they expect a current of which is too much, they need to pick a scale that maybe runs from 0 to 5. Then you check how are the divisions. If this is 1, this is 2, this is 3, this is 4. Then you check how many divisions do we have inside. If there are 10 of them, then you ask yourself that for 10 divisions represented by 1 amp. What about 1 division divided by 10 times 1? Then you will know that what is the expected value, like what is the expected decimal number of decimals you're supposed to record while using this ammeter. At times the ammeter may be in the range of 0 to 1, like that. The one that most of you tend to confuse, so that you have all this as maybe 0.2, normally 10 maybe 0.2, then this point maybe 4, then you have 0.6, then maybe you have 0.8, and then there is 1. Then you're supposed to check how many divisions do you have in between. If the divisions are 10, again, you ask yourself that for 10 divisions, I'm having 0.2. What about 1 division? Will represent how many? So you will see that it's about 0.02. So this allows you to record your readings into 2 decimal places. And of course, most of the practicals you'll be doing, we expect you to record that ammeter reading in 2 decimal places. Anytime you have any reading and you're doing your practical, and in your table, we have I there, of course, in amps, and your values are into 1 decimal place, 1.3, 1.2, 1.1. No, these ones are not accurate. It will be more of approximations. Most of the times, the meters and the range that you'll be using requires you to give 2 decimal places. So like if the reading was somewhere there, like that, and maybe that is the 7th division. So just check that 1 division was representing 0.02. Then how many do you have? 7 from the 0.4. So what about 7? You multiply and you'll get, I think, around 0.14, right?
Yes.
So when you get 0.14, then ulikuwa umefika wapi? You had taken it from 0.4. So you add that to 0.4 and you get 0.54. That's the correct reading you're supposed to enter or record in your table. And also, as you record those readings, normally we expect these readings to be recorded in a pen. So if you use a pencil, ensure that at the end of it, or you have time to erase. But to be more, never know, maybe the time will be so little. So always try to be accurate and have those readings. When you're submitting your work, they need to be in a pen, not in pencil. In pencil, you won't mark any work in pencil. And also I've said that they take note of the 2 decimal places. If it is exact, suppose the reading is exactly at there, where you have 0.8, it is exact. As you record, add 0 there, because you are dealing also with the accuracy of the measuring instrument. So in physics, any reading you record, the number of decimal places has another message that is sent to us. It tells us that which device did you use and what is the accuracy of the device. So that is very important to take note of. Okay. Any question on that? Any question on that? So make sure that for the sake of your practical, you know how to connect the meter properly and you know how to pick the scale. So there'll always be 3 terminals therein. There'll be one and the other one. So they'll be calibrated. If one is positive or one is black, the other 2 will be red. Then they'll be given the units 1, either this 2.5. So from there, if you connect yours here, you should use the scale that runs from 0 to 2.5. Somebody is making a nice comments. Kindly check for me that person. We can you can remove him from the meeting. Start.
Joshua Igar.
Let me get to know that person is making noise. I want to remove him from the meeting. Alikuwa nani? Who was the person making noise? Who was having the microphone on?
Clive.
Clive Maina, are you the one? Microphone on. All right, please let's try so that we all benefit. It's good to keep your microphone off. If you want to speak, you can turn it on. Then after that, you can switch it off. So so that don't interrupt. All right, so that is what we are talking about. So I think next time we'll have better readings of our ammeters and our current in future, when you're doing any practical involving this. So if we don't have any question, then I think we can proceed.
Excuse me, sir.
Yes, please.
I have a question.
Yes.
We've said that the SI unit of charge is Coulomb.
The SI unit of charge is Coulomb, yes.
Yes, and you have also said that by charges we mean electrons. So does this mean that 1 Coulomb represents a certain number of electrons?
Now, the concept of charge, the concept of charge of an electron it is something called an intrinsic property. It is a property of an electron. It is something like, which one? It's like something like a mass. Like, for example, your mass. You know, your mass is an intrinsic property, a property that you have. So charge is just a property of an electron. And actually, 1 electron have a specific charge of 1.6 times 10 raised to power negative 19 joules. So this is more of a property. If you talk of a charge, it's a property of an electron. So to be general, we normally just talk of charges to mean positive and negative charges. But when it comes to the electricity, the idea of electricity coming in, you only deal with the electrons. Why? Because we know that if we go back into an atom, we have the protons, neutrons, and normally outside, we have the electrons. So the one that can easily be dislodged and help us in conductivity easily for most conductors are always the electrons. So that's what we consider. The protons which are positively charged are normally held in the nucleus. So with them, we don't use them for electrical conductivity. So for electrical conductivity, we require to use the electrons, of which in any time, in any minute, if you connect, somebody is again, microphone is on. If you connect your circuit, there's a number, so many of the electrons will be involved. Actually, there's always, the total charge that will be involved is always Ne, the total. The total of them will always be Ne, where N, the total charge that's supposed to be involved here will be Ne, where N will be the number of electrons involved in that case, and E will be the particular charge, which is 1.6 times 10 to negative 19. So that will be the charge of that particular electron. So there is a number of electrons. So many of them always involved actually. We don't deal with only one electron. In one atom, of course, if you look at a small piece of copper wire, for instance, there's so many atoms there and there's so many electrons involved. So anytime you're having a conductivity, millions and millions of electrons are involved. So therefore, there's some more finer details about this, which are beyond our scope. Yes, but I don't want to get into them. There's something called current density and J, and which now brings all the details about the electrons, how they move, and bring the idea of the current, which is not in our scope of study. So are you answered?
Yes, thank you.
Okay, welcome. Any other question? Any question, especially on the idea of measurement of current?
Excuse me, sir.
Yes.
You said that right now, since we have developed this class, we should change the definition of PD and EMF. So what is the definition of EMF that we should be using right now?
The EMF, I'll come into it. It is our I think our last thing, but the definition of EMF is simply the potential difference. You can use the word potential difference, or you can use the word voltage. So any of the words, I know that those who prefer the word voltage because it's more general, and some people say that PD is specific, but it's more of the potential difference between the terminals of a cell when no charge is flowing or when it is supplying no current. That's a better definition than just saying that in an open circuit. You can talk of the potential difference or maybe the voltage across the terminals, between the terminals of a cell when it is applying no current or when there's no charge flowing out of it. That is for EMF, but of course I'll come to that. So that idea of open and closed, we can only accept it, especially when the question asked is to differentiate between. So when asked to differentiate between a PD and a EMF, that's easy. You can bring the idea of open and closed circuit. But in the question, just a single question, define PD, we expect to give the definition of the work that you in moving a unit charge from one point to another in the circuit. Or through a conductor.
Pardon the definition.
Definition of PD or of EMF? Which definition do you want me to pardon? The EMF or the PD?
EMF.
Oh, EMF. EMF, I've said, is the voltage.
EMF.
Yes, it is a voltage between the terminals of a cell. Is a voltage between the terminals of a cell when it is applying no current. When it is applying no current.
Okay.
Yeah, so though that is our last topic, so I mean our last topic, so maybe I think we shall finally come to it nevertheless. Okay, so we can proceed with the measurement of voltage now.
Excuse me, sir.
Yes.
When you talk about EMF being the voltage supply between the terminals and no charge is supplied, and that's technically the same as when it's an open circuit. What's so wrong about that definition, since an open circuit obviously doesn't supply any electrical charge?
The difference that there's one which is mature and one which is immature. That's the difference between the two definitions. One is a mature definition, one is immature definition. So the definition that belongs for Form 1, leave for Form 1s. I mentioned that earlier on. I mentioned it clearly that in Form 1, we don't want you to struggle. We give a very simple definition. We simply tell that PD is the voltage in a closed circuit, while EMF voltage and open circuit. Yes, it is very correct. I'm not refusing that it's not correct. It is very correct, but it's too simple for a senior student like you. You know, you are a senior student. You are our candidate in a few months' time. So, of course, I know you won't be penalized for giving that simple definition. That is, if you can't give the one that I'm giving, which is more comprehensive, you can give that one. Well and good. No worries. So, it is okay. You won't be crucified for that. Is it okay?
Yes, thank you.
Okay, so measurement of voltage, maybe quickly. A measurement of voltage, we can, voltage you measure using what you call a voltmeter. Voltmeter is the device used for measuring voltage. So this is a device. It's a voltmeter. Actually, the idea of voltmeter and ammeter, there's a concept they're using. The concept of electromagnetism, magnetic field. There are more of some coils that just move around, but you can check on that, how the principle through which they work. But a voltmeter is the device that we use to measure the voltage. And this one will always be supposed to be connected normally across or in parallel. So you connect a parallel because this device normally draw a lot of current from the circuit. It's a device that has a high resistance. A high resistance will offer a lot of opposition to the flow of current. So if you place it to be in series in the path of the current, then it may draw a lot of current, and therefore, it will offer a lot of opposition to the flow of current. So in that case, we connect in parallel, and these are to look like, if these are maybe the dry cells we're using, 2 of them in a circuit. So the circuit continues. Maybe we already saw that we need to connect the ammeter in series, so that can be our ammeter. Then this can be maybe our bulb. If you like, you can proceed and have a switch if you like. Those switch at times may not be necessary because it just adds resistance in the whole thing. It also withdraws some small current from the system. But also good at times, some experiments, because they help you to control, especially if you are to vary the current through by moving maybe a jockey through a resisted wire. It's always good to have the circuit off first, move it to the next place, then return it. Now the voltmeter is connected here, so you can have it here like that. So when you have it there, it will allow you to do some 2 measurements when it is there. It will allow you to do a measurement of EMF. You can measure EMF from it. We shall talk about this, of course, later, but now EMF will be the voltage that is just there when this circuit, when this switch here is still open. So there's no current flowing. Of course, when there's a junction, there's an opening like this one here, the current is not flowing through the external circuit, that is through these loads you are having here. There's no current flowing. So in that case, the reading that we are going to have will be the EMF. And maybe if there are two dry cells like that, we expect a EMF around 3.0 plus or minus 0.2 volts. That's what we expect. So it can give you, if the cells are too new and some of them are very powerful, they're like the ones used in your practical when you are for the end of term, they are very powerful cells. Of course, some of you are even having a reading of 3.3, 3.4, and we marked them right, I think, because we understood. But normally, under standard conditions, we expect that those cells, because each of them have an EMF of 1.5, so they should add up, because we normally have them in series in most of the experiments. So if you multiply that by 2, then they give you 3.0 volts. So it can go to 3.1, 3.2, or even can be less, 2.9, 2.8. All of them are correct. But then now, once the circuit is now complete and we have closed our switch there, then this voltmeter will give a reading, and the reading will be called the PD, the potential difference now. And that reading will always be lower than the EMF. So if at all in your experiment, you are getting the EMF to be 3.0, then you are kind of writing for us PD to be 3.4. That's not practical. That's not possible. The PD have to be lower than the EMF. So this PD will be maybe, say maybe 2.8 plus or minus 0.2, like that, based on your previous reading that was there. So if the EMF yours was 3.0, we expect your PD to be around 2.8, maybe 2.6, something like that, something low. So that is how we use the voltmeter. Also ensure that you connect it properly, so that you connect positive to positive. So it also have those terminals, the red and the black. The red are always the positive. So that positive one will always go to the side of the positive of your battery. Like the negative goes the negative, like that. So that's how we're supposed to connect, so that if the current has to come, it has to get through the positive, then the negative, like that, following a proper flow that is expected. So, and again, on this one, also make sure that you pick the appropriate scale, and make sure you understand the scale you're using before you proceed to use it. The scale is very important, so that you have your readings proper in the proper decimal places. So any question on that? Yes.
Excuse me. Why are we saying that the PD has to be lower than EMF?
Okay. So the PD have to be lower than the EMF because of something called internal resistance of the cell. Internal, let me raise it here. This again is should be our last subtopic. Internal resistance of the cell. Now, normally cell also have an opposition to the flow of current. A cell is also not a superconductor, so it also have some opposition. So because of that small opposition, of course, that is there inside there, it will always lower the EMF to be the voltage to be a reduced value. And because this internal resistance is always something very small, it's always not very big. The PD, the voltage we want to drop by that much value. Of course, we shall come to this later on. We shall see that the EMF is given us the IR plus the I small letter r. So this small letter r is actually what we call the internal resistance of the cell. So E is equal to, this one is give you V, IR is just V, and then IR, where this V is what you call the terminal voltage. So this is basically the PD now that you are measuring. And then this is the EMF. So you can see that to get the EMF, you have to add the PD plus some, this one is called the lost volts. Lost volts. So plus some lost volts. And these lost volts, they're simply due to that internal resistance of the cell. So that's why it is reducing the value of the EMF just by something. So this is the equation that we're supposed to know. Maybe you can derive it later. So this is the loss. This is a lost volts. This is a terminal voltage. Or there's the PD, and this is the EMF. And that's why so from this equation you can see the reason why the values have to vary.
Thank you.
Okay, welcome. So any other question? Or we can proceed? I think we need to proceed so that we are able to cover all that we're supposed to do. Now, there's something called connection of components. The connection of components. Let me see how much space we have. Very little. So we can begin erasing. So connection of components. Now components can be components here or just loads. In general, we can talk of them as being loads or resistors. Anything that requires, of course, some current for it to operate and all those things. But one of them can always be the bulbs. Well, that one you have encountered in, again, in current electricity one, in cells and simple circuit. We encountered a bulb, and a bulb can be a load. So we are supposed to check on when we connect the bulbs, either in series or in parallel, how is current being distributed in them, and how is voltage being distributed in them. A proper understanding of that concept will ease our work so much when you come to now the connection of resistors. Whether your resistors are in series or in parallel, how they will behave. They behave exactly the same way as we are going to check on the bulbs. So let me have this, for instance. I think that space somehow enough to work with. So the connections of components. Now let's begin the components being in series. And I'm only interested in two things. How are the current distributed and how are voltage distributed? So simple, let me pick the bulbs and put them in series. So if you have a bulb will be there. That's one bulb. Then you connect that bulb to another bulb like that. Then that bulb to another bulb like that. Then for simplicity, let me just talk of directly, you connect them to a source. I will modify this diagram in a short while. Let me just connect them to a source here. Let me give them 2 dry cells so that EMF is a little bit higher, like that. So what we expect now, allow me assume that the bulbs maybe are identical for simplicity, for quicker understanding of this. The bulbs maybe are identical. So you have bulb 1, bulb 2, bulb 3, bulb 4. So we may be interested that in this bulb 1, bulb 2, and bulb 3, what is the current flowing through them and what is the voltage flowing through them? So if you want to know the voltage in the whole system, is simply to come and put in a voltmeter here. A voltmeter there. Voltmeter there will tell you the amount of voltage that is there in the whole circuit. And of course, once you know that, then you can also come and decide to place a voltmeter in each of these bulbs. So there's a voltmeter there across each bulb to just give the reading there, a voltmeter there, and you can place another voltmeter here, like that, so that you can know what is the voltage across a voltage drop across the first bulb, voltage drop across the second bulb, and voltage drop across the third bulb. So if you do this experiment, interestingly, you will realize, number one, that the voltage drop across each of these bulbs, if the bulbs are identical, will be the same, but their sum, their total, will total to the input voltage, the voltage being supplied to them. For instance, if these are 2 dry cells, so that the voltage is around maybe 2.7 volts, that's what we are having here. Then if you measure the voltage, if the bulbs are identical, you realize that they'll share it equally, so that this will be 0.9, 0.9, and also this becomes 0.9, like that. So that the total voltage drop across each of the bulbs will add up to the supply voltage of 2.7 when they are connected in series. While the same current that is flowing, there will be the same current flowing through them. So if the current leaves from this point A like that, There's no any junction through which the current will branch to. There's no any junction. So that current will just come in, flow through the first bulb like that, the same current, second bulb, the same current, third bulb, and then like that. So it will be the same current. So when you have devices in series, the first thing you need to note is that the same current, they have the same current flows through them. The current is the same. The same current is flowing through them, while the voltage drop between them can differ. For instance, if the bulbs were not identical, identical here means, what do I mean when I say identical? Identical means that the resistivity of the wire, that is the filament, is basically the same, so that they have the same resistance. They offer the same portion to the flow of current. Then if you see the bulbs are identical. But also, some bulbs cannot be identical. Like for instance, when I'm mentioning this, that when it comes to the resistors, which will be different values, we understand what's happening there. They may have different voltage drops. It doesn't matter. But the total, the sum of voltage drop across each will be the same as the one from the supply. So the sum of voltage drops across each is equal to the supply voltage, to the supply. The voltage is being supplied to them, supply voltage. So if the supply voltage is 10, then if you add those individual voltage drops, it will add up to that 10. So this is the two things that I'll want you to remember and not to forget at any instance. If you want to understand the idea of resistor networks, how to simplify them and solve the current across anything, you have to remember that anytime you're having devices in series, the same current flows through them, then the voltage drops across them can differ, but the total sum should be the same as the one that was being supplied. That's number one thing to note when they're connected in series. Now, that is something you can note somewhere. Then number two, now I want us to connect our devices in parallel. So our devices connect in parallel, like for example, our bulbs there. In parallel means that, of course, all of them, their heads, all of them are together, the tails are together, like that. So in terms of a diagram, it will look like this. That was can be our first bulb. The second bulb can be there. Suppose I'm using 3, another bulb there. Then I connect all these together like that. Connect all these together like that. Then all this, I give them to the supply voltage like that. So again, I may be interested to know what is the amount of voltage drop across each of them. Then also, what is the current? So to begin with, the first one is the voltage drop. So for voltage, you can do this experimentally in the lab. Just come and connect a voltmeter across each of the bulbs. A voltmeter can be given there for that first bulb, and a voltmeter given there for the second bulb, and a voltmeter given there for the third bulb. Then you can also have a voltmeter to measure the total voltage in the circuit. The total voltage in the circuit, for instance, let's assume that it is 2.7 volts again. Then something interestingly is that each of these voltmeters, each of them will give a reading of 2.7. What does it mean? It means that you have the same voltage, the same voltage flows through them. And the reason for this is because they're in the same potential. Look at this point and this point. All of them are within the same potential. So regardless of whether you are placing yours where, regardless, it is under the same potential, and therefore the voltage across this, let me use the red one here. So anything that is in between these is in the same potential. So anything that will connect them in parallel will always have the same voltage, which is supply voltage. So the voltage will be the same, but the current cannot be the same. Why? Because of anyone who can try. Why are we saying that the current cannot be the same? Because of what? Are we still there? Ama niliwapoteza?
Yeah.
We're still here.
Okay, very good. Because of the junctions. You people, you have never heard of that, junctions. So check, the current will be moving this way, coming from the positive terminal, and then comes, get there. Then if you reach this point, it's like you are walking, and you reach, or you are coming from the gate, the Alliance gate. And of course, at the first junction, there's one that goes to the sanatorium, one that goes to the teachers, or go to the school farm and all that. Then one goes straight. And so you have a junction of 3. So that's the same thing that is happening in this current here. It is coming here, it meets 3 paths that it can take. And each path requires its attention. So what will happen is that it will divide. Some will go through this path, others will go through this path, and others will go through this path. With the path with the less resistance having the highest amount of current. No path will have a current of 0. It can be very small, but it will be there. So the highest one with the lowest current will have with the lowest resistance will have the highest current. So it will go through this junction. So this current moving up to the first resistor will get there like that, then come here and then rejoins. Then the one that passes through this one goes, get there, then rejoins, again, gets there, up, rejoins, and then come back to the negative terminal like that. So because of that, the currents will be different. But notice something, the same current that comes in at this point must be the same current that comes out at this end point like that. And actually, this is summarized by the Kirchhoffs. There's somebody called this one here. You can call it Kirchhoff or Kirchhoff. It is beyond, okay, you will meet it in future. But it's a very basic thing about the junction law, whereby we say that the sum of currents that is getting into a junction must be the same as the sum of the currents that are coming out of a junction. So it means that, so if you add, if the current that was coming in at that point, let me bring the idea of the junction down here. So that is the junctions that we have, the paths. So the current will be coming in at this point. Then at this point, it gets there, get down there like that, proceeds, get down like that, then gets out. So if the current that was coming in was 2 amps, for instance, if it reaches this point, if maybe 1 amp goes through that, then meaning that maybe up there is going with maybe 0.3 amps, then down here will be 0.7. So that the total current that is coming out must be the same total current that is coming in. Then as we get in at this second junction, this second junction here, we'll be having current coming in, current coming in. Up here, 0.3 coming in, katikati 1, then 0.7. The 2 combine and join to give back the 2 amps again, like that. So back to my circuit up here. So the current will be different, but the sum of current in the individual load or component must be the same as the total supply current, the total current that is in the circuit. So the sum of the currents will be the same as the total current in the circuit, So this is again something which is very fundamental for you to understand the resistor networks. And whether it is in a voltage, in series or parallel, these are the most important concepts to remember. So we have to remember this one, number 1, and also you have to remember this other one for the sake of series and also for parallel.
Excuse me, sir.
Yes.
Why do we say that in series, the current passing through the identical bulbs are the same, while in parallel, they are different?
Because of the junction, I've just mentioned that the idea of the junction law, the Kirchhoff's law, or the Kirchhoff's law. Remember here in series, there's no the current does not branch anywhere. It doesn't have multiple paths. The path that the current have to follow is exclusively one. So because of that one path, it has just to go through the same can have to go through these bulbs. There's no any other path that it can follow. While in this parallel arrangement, the current will be coming, then we'll be finding that it comes, of course, then finds that there's a different paths from there. So there's a path there, a path there, and a path there. So each path have to be followed by the current. So in that case, they will disintegrate. Some will go there, others go there, others go there. So in that case, this one, of course, if at all if at all, maybe if I get the question right, if at all the bulbs are identical, they're the same, then in that case, what happened that they will share that current equally. So if the current was maybe 1.2 amps, then in the first one here will be 0.4, then here 0.4, then 0.4, like that. But the total sum, if you add finally, should be the same as 1.2 that was coming in, and that will finally come out. Now, the reason why I was also stressing on the fact that they're different because of the resistor networks. The resistors we'll be dealing with will never be the same most of the times. They'll be different. So I was just trying to bring to your attention that because of that different resistance, there'll be a part that will have more current, less current, and maybe average current. But the total current should sum up to the current that is in the whole circuit.
We may do the roll call now. I request you to give us some 1 minute or so.
All right.
So,
okay.
Thank you. So, boys, check on your screen. You should see a roll call display. Pick it and submit. We're at 130, 140 now. We are at 185, 87. From 4A, only 24 of you have done. B, 21 of you. And I think I have a shoot. G has only 12 students over. And Q, I can only see 13. But the rest have big numbers, which is a good way. Being K is the highest, so far with 29 of you from 3K. You can see 29 of you have already confirmed attendance. B at 21. The last one is still from 3G at 12. G 12, 3Q 13. Those are the smallest numbers I can see. Okay, I think we should bring it to an end now. Thank you, Mwalimu. You can go on. Appreciate it.
All right, thank you. So now are we together up to there, or there's still any other question?
Yes, sir.
Together.
I hope it is clear the idea of that concept of same voltage, same current. So what you need to remember, especially for us, to help us understand the idea of resistor networks.
Yes, sir.
All right. So with that in mind, just keep that in mind. I will mention it. We will need that concept right now in a few minutes when we are now dealing with the resistor networks. We'll require that knowledge that when you have components connected in series, same current flows through them, then the total voltage, of course, the sum of the voltage drops across each of the devices is equal to the supply voltage. And of course, if the devices are identical, they'll have, of course, equal voltages, which finally sum up the total one, of which in reality, most of the times they may not be identical. So just have to calculate their values, then add up together to give the total that is required. Then, of course, then I've said also in parallel, ensure that to know that everything that are in parallel, they're always under the same electric potential. So for that reason, they will always be having the same potential difference or the same voltage. And then for current will not be the same, it will always differ based on the path. So the path with the less resistance will have more current and all those, but finally, the total sum of those currents have to add up to the total current in the circuit, or the total current being supplied in the circuit. So with that, we can introduce the idea of Ohm's law before we check out the resistors. So let's check on Ohm's law. Now, I think in 18 something therein, Ohm was able to devise for us a law that is being obeyed by as current flows through a conductor. So when you have, of course, you can derive the law through an experimental venture. You just need to do some experiments and vary the current as you measure the voltage, or you vary the resistance. Then you vary the resistance, you will measure for you, vary the current, and then the end result, the voltage is varied. Then you plot a graph and then come up with the result. But the law is more of that, again, somebody is having microphone on.
Brian
Nyangwara, I will let me try huyu hata tupigia kelele. Yes, that's done. So allow me just to state the Ohm's law, then maybe we can talk about it. So you say that if you're having a conductor, of course, that is your conductor again, maybe AB, that is a conductor, and that are the points. The conductor is, of course, connected to a potential difference, and all that is there. Then if we keep any factors constant, the factors, physical factors kept constant, and also you keep things like temperature. And now temperature normally affects the resistance, and finally will affect the current and all that. That's why you have to keep them constant. So if they're kept constant, you're doing that experiment in maybe a room where the temperature is constant and any other physical factors or conditions are constant, then the current that is flowing through the conductor is directly proportional. So the current that will be flowing through the conductor is directly proportional. Directly proportional to the potential difference across it, to the PD, or the potential difference across it, provided the temperature and physical condition are kept constant. So that is the Ohm's law. So you need to know how to state it, and you should state it as the current flowing through a conductor is directly proportional to the potential difference across it, provided temperature and other physical conditions are kept constant. So some such laws, you normally state them verbatim, the way they are. Don't come and bring gymnastics. Now, the rest of us who like gymnastics, no one has asked you to state and specify the physical conditions. So don't specify. Don't come and say that other physical conditions like pressure, etc. No. Just leave it open like that. Just say that the current flowing through a conductor is directly proportional to the potential difference across it, provided the temperature and other physical conditions are kept constant. So mathematically, we say that we can use maybe that potential difference, call it V, is directly proportional to the current. Of course, you can always commutate. You can talk of I proportional to V or V proportional to I. It doesn't matter. Kindly mute. Tell that one to mute. Nani?
Brian Nyangwara.
Ameingia na
Brian Nyangwara.
kelele tena.
Nyangwara.
I have muted him for everyone, so that is better. So V is proportional to I. So that is the relationship that Ohms is giving us. So V is proportional, directly proportional to I, not T, I mean I to the current. So normally to remove this idea of proportionality symbol, you have to bring a proportionality constant. And that constant, in this case, let me just bring it normally, the way we do in mathematics, it might be some Ki like that. So that is the proportionality that comes in. So V is equal to Ki, and this K, it has a specific name. It's a property of the conductor, and that property of the conductor is called resistance of that particular conductor. It's a specific property which we call resistance. So instead of using K, we normally use R to mean resistance. So V is equal to Ri, which normally I like rewriting it as V is equal to IR. So this is the idea of Ohm's law that you're supposed to know. So you're expected to know this formula and also to know how to state Ohm's law. So V is equal to IR is the Ohm's law formula, which from here you can draw your triangle again and have all the formulas to relate. V is equal to IR. So from here, if you're looking for current, you talk of voltage divided by resistance. And if you're looking for resistance, you talk of voltage divided by current. And for these short formulas, if you're using them, it's always just good to write them in words. There's no problem harm in that. Though you're also allowed to use symbols, but if you're using the symbols, be very careful. If you talk of something like small letter R, it will be something else, internal resistance. Yes. So be very careful if you have to use the symbols. So that is the idea of the Ohm's law. And this R here, which you have said is resistance, it's measured in ohms. Is measured in ohms, and that symbol is this. Now this capital omega, we normally have a small letter omega, which we normally write like this. Then we have capital omega. So the capital omega is the one that we use for ohms, for the SI unit of resistance, which is ohm. Now, if you have to draw a graph, you have done just the experiment, and you have to draw a graph that is representing this idea of Ohm's law. If the graph is this way, if you have your graph as V, or voltage in volts against current in amps. Now this graph will always be a straight line because it's direct proportionality. So it will be a straight line passing through the origin. That is, so it has to be a straight line passing through the origin, of course, direct proportionality. And of course, it obeys the equation of a straight line. So this graph here may have some meaning for us. Anytime you draw a graph in physics, try to understand what does the gradient represent and what does the area under the graph represent. And if I told you a graph that is cutting an X or Y axis at a specific value, you'll ask yourself, what does the Y-intercept represent and what is the X-intercept representing? The physical meaning of it in physics. So like for instance, in this case, if you had to find the gradient of this graph, the gradient of course, normally we talk of the gradient of the slope will be the change in Y, and in our Y-axis you have the voltage. So we talk of change in voltage divided by the change in whatever is in the X-axis, which is our current change in I. Now you must write that. Please don't talk of change in Y, especially in practical, where that the formula for the slope or gradient has a one hallmark. If it's unpractical, for instance, let me digress a little bit. It's just a practical. You have just maybe done a product of t squared, is more of the pendulum. S squared against maybe L, and you've just now asked to find the slope. Please don't talk of changing Y over changing I. This being general, this is for mathematics. So if you must write it, then you have to come and finally write for us in physics. What is on our y-axis? In this case, it is t squared. So talk of changing t squared divided by changing L, 1 whole mark. So don't always lose that 1 whole mark like that. So always ensure that in our physics, the slope, the axis has names. So talk of changing v over changing I, then get that slope, there was the slope, get that slope, and you'll find a value for it. Again, our slopes in physics have units. They're not dimensionless, unless otherwise. But in most cases, they may have unit. For instance, in this case, you check, our slope is given as change in v over change in I. Then you ask yourself, in physics, that you know, what does v over I represent? This formula gives what?
Resistance.
Resistance, very good. So the slope is always equal to the resistance of whatever you're investigating. If it is a Y or something, resistance, like that. So because of that, if you get the value finally of that your slope, maybe it is 2.3, you have to give it a unit, and the unit will be ohms, like that. Again, if it's for the practical setup, we mark half a half. We'll give you a half a mark for the value, and then half a mark for the unit. If you give wrong unit, you lose the whole 1 mark. And if you leave your answer without a unit, you get half a mark. That's how we mark them in practicals. So that is that. Now that is if you draw a graph of V against I. If you were to draw a graph of I against V for the same, the graph of I in amps against V, of course you're supposed to write in volts. Then the graph will still be a straight line, of course, passing through the origin, and now the area under, the gradient of the slope, gradient will now be change in I over change in V. Please be consistent. It has to be always change in Y. So first being whatever is in the Y, V is change in I over change in V. You'll get a value, of course. But if you check this quantity that is here, the quantity we expect to get here, it is more of the reciprocal of whatever we have here. So the answer will be the reciprocal of resistance. So if somebody asks you to find the resistance from a graph of I against V, then get the slope, or you can give them a statement. Tell them that the resistance is equal to the resistance. You can tell them in writing. Somebody will know that you know a lot of physics, is equal to 1 over the slope, or just say the reciprocal of the slope. These are very important things. So that you'll find the slope. Once you get the slope, you find it's reciprocal, because this slope is just 1 over R. And 1 over R is something called conductivity. Anyway, we shall, no, not that. It's just a reciprocal of the resistance. We shall come to that idea later. Instead of residual conductivity. So they just give the reciprocal of the resistance, and its unit you can get. What is the unit of that? The unit will be
reciprocal of ohm.
Yes. So how do you call it? How do you write it in symbol?
Siemens.
Yeah, it can be Siemens or
Ohm power
like that.
inverse.
Per ohm, not ohm meter. Ohm meter is something else. Just like that. It gets a zero ohms, because for ohms it is for just ohms, so just the zero of ohms, which is that to mean it's reciprocal, or per. Anyway, so that is that. If you draw that graph that way. Now I will need to give you an example so that you have something to do a little bit. So write this. A simple example involving use of that Ohm's law, and just this one. say that a current of 1.2 amps flows through a conductor whose resistance a current of 1.2 amps flows through a conductor whose resistance is 3.0 kilo ohms. Determine the voltage drop across the resistor. I mean across the conductor. So yeah, that is a question. A kind of 1.2 amps flows through a conductor whose resistance is 3.0 kilo ohms. Yes. Determine the voltage drop across the conductor. Although that conductor can be a resistive wire, it can be something. I'm just being general. It can be even a resistor itself. What is the value? What do you get?
3,600 volts.
800.
Uende na afu mcheze hizo vitu za bedroom.
3.6 kilovolts.
Nataka vitu zangu.
Sample is getting 3.6 kilovolts.
3,600.
3,600 what? Goats.
Yes.
3,600 volts.
Okay.
3,600.
Okay, thank you. Very good. So the formula says that V is equal to IR. If the question has 3 marks, the first marking point is on that particular formula. V is equal to IR. So from there, we ask, what are we looking for? We are actually looking for the voltage drop. So V is equal to the current that is flowing. The current is given to be 1.2. So just that 1.2 times the resistance, and they must always be into the base SI unit. So this is 3.0 kilo ohms. So you have to convert it into ohms, and kilo means 1,000. So that is the same as 3,000 ohms. So from there, you can get your answer directly that V is supposed to be 3,600 volts or 3.6 kilovolt, as somebody had stated like that. That's okay. So that's just a small exercise to jog your brain. Something which I can go on quickly is something to do with ohmic and non-ohmic conductors. This is simple. A ohmic conductor, let me write it here. Ohmic, from the word ohms law, ohmic conductor. So a ohmic conductor is similar conductor that obeys Ohm's law. So, and Ohm's law means that if you draw a characteristic curve or graph, like a graph of I against V, it should always be a straight line. So that one obeys Ohm's law. So their graphs will always be the one that will always give you a straight line like that. Those are ohmic conductors. They just obey Ohm's law, and that's direct proportionality. While non-ohmic are now the ones that does not obey Ohm's law. They are conductors that does not obey Ohm's law. And An example of them is a semiconductor diode. Now, semiconductor diode is one that its resistance will always decrease with increase in temperature. So the graph normally look like that, semiconductor diode. So this I against V, maybe like that. So it doesn't obey Ohm's law. So even something like a thermistor, even a torch bulb, that filament will not always obey Ohm's law. It obeys at the first, then later on disobeys, because as it works, the heating effect, temperature increases, and therefore the resistance, of course, will always increase. So the current will always decrease after some times, so that it doesn't obey Ohm's law. It ends up being a curve. So those are called non-ohmic conductors, the conductors that does not obey Ohm's law. And you can have, you will check and see a number of them. There are examples there and their graphs and how they're done. So maybe back to that idea of electrical resistance that we had mentioned before in our graphs. So electrical resistance is simply, we can say that is the opposition offered to the flow of current by a conductor. That's what we call electrical resistance. Electrical resistance. So we define it as the opposition offered to the flow of current by a conductor. So when current is flowing, it is being opposed, that being resisted not to flow. So that impedance is more of resistance. That opposition is a resistance. So it will always there, of course.
Excuse.
Yes. Yes.
Could you explain the meaning of impedance?
Impedance is simply opposing something. Impeding is like opposing. So it's the same thing, it's just more of a resistance. Though that term we normally don't use it most of the times when dealing with resistors. We use it when now dealing with some complicated, some circuits that involve inductance, involve capacitors, involve resistors. When you combine, is when you normally bring the idea of impedance. But generally, vaguely speaking, just more of that opposition anyway. To impede is like to oppose or to resist. So there's nothing much.
Thank you.
So resistance, electrical resistance. So the fact doesn't affect this resistance of a certain, maybe you can look at in terms of a wire or maybe of a conductor. We have what you call the issue of the temperature. Of course, one of the main factors is the nature of the conductor. Is it a metallic conductor? Is it an unmetallic? Is it a semiconductor? Which kind of conductor is it? So we need to know on that. Then once we check on it, maybe you're now dealing with the metallic conductors, for instance. Suppose you're dealing with a metallic conductor, and a metallic conductor, I can maybe think of maybe a certain wire. So suppose I have a certain wire, the fact that will affect the conductivity, the resistivity or the resistance of that particular wire will be, number one will be the temperature. The temperature. So the temperature will always affect such that when you increase the temperature, what happens at the kinetic energy? Of course, as we have said, that anything is made up of atoms and all those are there. So when you increase the temperature, the kinetic energy, of course, of the atoms increases, and therefore they start vibrating more vigorously. So when they are vibrating and having all those motions here and there, they tend to oppose or impede the electron that is flowing through to bring the issue of the electrical conductivity. So when that electron is being impeded or being opposed, as it moves by, it leads to a decrease in the amount of current that we have. So in that case, we're having resistance, the idea of resistance coming in. So temperature, increase in temperature leads to an increase in resistance and then decreases the current in the circuit. And that only applies for metallic conductors. For things like semiconductors, they increase the temperature, they are very happy because the electrons are now able to jump from where they are to the conduction band, and they are very easy, very happy. They can now bring the issue of conductivity easily. So that's how temperature affects. So temperature affects that. Now, assuming that we keep that temperature constant and the nature of the material is the same. So for instance, let's pick copper wire, for instance. To pick copper wire at the same temperature, and of course the copper, of course, now is the same material. Other things that will affect the resistance will be the dimensions of this copper wire. And in terms of dimension, we'll have something called the length of that wire or that conductor, and also the cross section. The cross section, or you can call it the thickness or the diameter. The thickness, cross section, or the diameter of that particular wire. So for the sake of the length, of course, when the length is increased, when it is much longer, the resistance also increased. When increase in length, also increases the resistance of that particular conductor. While for the sake of cross-section, it is inversely proportional. When you increase the cross-sectional area, then the resistance decreases. And of course, the reason for that is because when you have a larger cross-sectional area, for instance, this is a conductor and that's this bigger diameter, means that there's so many electrons per unit area, or per unit, whichever it is you want to take. When there's many electrons, and electrons are the ones that we require for the conductivity, it will become a very good conductor. So that's why when you increase the cross-sectional area, the resistance decreases because you have more electrons which are available for conductivity, and therefore it will be very easy to conduct the current. So in all this, in terms of the dimensions, if you were to bring in a mathematical relationship to relate them, then we talk of the resistance of the conductor. The resistance of the conductor R, we have said that is directly proportional to the length, and also we have said that it is also inversely proportional to the sectional area or diameter of that particular. Somebody's microphone is on, and the person is also working, or what's happening? Is it true? Okay.
Yes.
Sawa. So we can proceed. So we need to combine these two things you have just mentioned here. We have said that the resistance depends on the length and also depends on the cross-sectional area of that particular. But these two combine, and generally we call them dimensions of the conductor. Generally, the dimension of the conductor. But please don't state that. If you have to write that word in an exam, you have to give example. Don't just say dimension, say like length. And that's why we prefer that you just state them. Like for instance, one of the questions you asked, you are told that there's so many factors that affect resistance of maybe a resistor, and therefore you can always state them. We have the idea of the temperature, we have the idea of the thickness or cross-sectional area, and also the idea of the length of the conductor. Now, mathematically, how does
length affect resistance?
Oh, how does length affect resistance? Let's see. These two conductors I have here, this A to B, and also this is A to B, like that. So suppose you have an electron. Let's assume that you have one single electron. It has to move from this point here, and the electron is there. It has to move all the way to B, and there's also another electron here that has to move from here to here. So between A and B, which electron is going to face a lot of opposition on the way? It's going to meet a lot of things to oppose it on the way. Is it the first one or the second one?
First one.
The first one.
The first one, because it has to travel a longer distance, then it also means that it has to face a lot of opposition, because it's always not a walk in the park. Remember, there's always what you call the electrons. Actually, the kinetic energy is always not at zero. So normally there's a lot of vibrations going on. The electrons are moving. The atoms are always vibrating. So it's always not a really easily walk in the park that you just easily move through like that. So you have to always meet some opposition on the way as you go. So if you have to travel a longer distance, of course, more position, and therefore there's increase in resistance. Therefore, current is much reduced.
Thank you.
Okay, welcome. Now, where was I? Okay, we are here. So we want to combine this into one statement. And one statement will be that R, or the resistance, is directly proportional to length, but also it's called joint variation. Is jointly. So it's directly proportional to L and also inversely proportional to the cross-sectional area. So to take out the issue of the proportionality symbol that we have here, we have to bring in a constant. And that constant in this case is not just any other constant. It is a constant which is called resistivity of that particular conductor. That resistivity, the symbol is something like this. That is the symbol we're using for density. It is called rho, maybe rho. So L over A, like that. So this is a constant. Just a second. Now this constant here is called resistivity. Resistivity of that particular material. Then this is length, and then this is the area, like that. So the resistivity is simply the measure of the position of that a conductor offers to the flow of current. That numerical value, that numerical measure of that opposition or that position being offered to the flow of current is called resistivity, like that. And resistivity, of course, the higher the resistivity, the higher the resistance of that particular conductor. So if you want to have a nice conductor which have very less resistance, then you have to ensure that resistivity value is very small. Like for instance, aluminum, or even something like nichrome wire, their resistivity tend to be very small. But some things which are which are poor conductor or non-conductors have very great high resistivity with them. So yeah, that formula again is very important for us. So let me rewrite it down here. Then I change its form using subject change. I change the subject. So the formula we have just shown and derived there as R is equal to resistivity times the length over the cross-sectional area. Now this formula, you have to remember it. It is important for you to make resistivity the subject of the formula. So resistivity from here, you can cross multiply. You can cross multiply here. You'll have resistivity times L is equal to RA. Then to get resistivity alone, divide here by L, also here by L, so that you'll have resistivity is equal to R or AR if you use the alphabetical order, divide by L, like that. So this is the resistivity, how you calculate the resistivity of a particular conductor. You check the cross-sectional area times the resistance and then divide by L. So from here, you can even get to know the SI unit of resistivity. So let's derive that SI unit quickly so that we know what it is. Now, the SI unit for area is, what is the SI unit of area?
Meter square.
Square.
Meter square.
It is square meter, not meter square. We square the meter, we don't meter the square. That okay? So in words, we talk of square meter.
Square.
Yes, you square the meter, you don't meter the square.
Yes.
Eh? Mtu anasema uongo.
Yes.
So I've said it is square. a square meter, like that. You square meter. No, you don't meter square. So area will be meter times meter, because that. Then for resistance, tumesema ni nini? For resistance, ohms. So we allow ohm there. Then we divide by, down here is length. So what is the unit of length?
Meter.
Meter, not meters. Meter. Yes. So from here, you can disintegrate it. M and M will cancel. Then you'll have the unit remaining as ohm meter.
Ohm meter.
Yes, you can do the ohm, then M. So this is called the ohm meter. Ohm meter. Ohm meter. That is the SI unit, ohm meter, of that resistivity, like that. Now we also have something called reciprocal of resistivity. And the reciprocal resistivity give us something else called what? What is the opposite of resistivity? Anyone? Conductivity. Very good. Conductivity. So conductivity and the reciprocal. They're not the same things. They're reciprocals. Conductivity. So this conductivity is simply 1 over the resistivity. Resistivity, or the reciprocal. If you define it, just the reciprocal of resistivity, the reciprocal. So that the conductivity, which we normally use a symbol of, I think this one here. Anybody know the name of this symbol?
Joules.
At joules.
Sigma.
It is this. This.
Sigma.
Very good. Somebody knows it somewhere. Sigma. So we have that as the symbol for conductivity, and is always 1 over the resistivity. So the resistivity and conductivity are reciprocal to each other. So meaning that whatever is whatever is a good conductor will always have a bigger value of conductivity but a smaller value of resistivity. That's important for you to remember. That the good something in conductivity, the poor it is in resistivity. So it has to be reciprocal. A higher value of resistivity translates to a lower value of conductivity, and a higher value of conductivity translates to
lower value of resistivity.
Very good. So the SI unit of this you can also get, it will be the SI unit will be 1 over ohm meter. So it will be like that, per ohm per meter. Per ohm per meter, like that. Just we are taking the reciprocals of them. A quick example for you to calculate.
How do you define resistivity? An exam setup.
In an exam scenario, you want the definition for an exam scenario?
Yes.
Yes.
But I mentioned that. I mentioned it. Somebody was not just kidding. I mentioned it. I said that resistivity is simply the measure of the opposition to the flow of current. What did I say? Let me write it for you here. The measure of opposition offered.
Of the opposition.
Not opposite, not of. The measure of opposition offered by a conductor to the flow of current. Offered by a conductor to the flow of current. To the flow of current. So it is now the measure Now resistance is general. So that measure of that value is more of resistivity. While now for conductivity, you just say it's the reciprocal of resistivity. So that numerical measure, for instance, for example, the measure of resistivity for aluminium. For aluminium, Al is about 2.8 times 10 raised to power negative 8 ohm meter. So this is the measure of its resistivity. You can see this is quite small, right?
Yeah.
Yeah, quite small. So because of that small value, that's why it is one of the good conductors, because of its small value of resistivity. And for other things, like for instance, and I wanted to compare and tell me which one do you think is a good conductor. Aluminium, I've said, is this. Then I give you nichrome wire. We'll be using this one maybe once in a while in the lab, or Constantine. Nichrome wire have a resistivity of around 1.0 times 10 raised per negative 6 ohm meter. That's the resistivity. So which one is a better conductor between the two, between nichrome and aluminium?
Nichrome.
So which one is a better conductor?
Aluminium.
You are interesting. And somebody is saying nichrome, somebody is saying aluminium. You put, hey, okay. Which is a better conductor between the two? I've given you the values of their resistivities.
Aluminium.
It's
Aluminium.
the value of
Aluminium.
resistivity of nichrome is much bigger.
Aluminium.
Very good. So aluminum have the bigger resistivity, and I say that the bigger the resistivity, the smaller the conductivity. And the smaller the resistivity, the bigger the conductivity. So aluminum, as you can see here, it has a very, very small value of resistivity. Hence, it is a very good conductor. So if you are to get the value of its conductivity, you simply need to take the reciprocal, and you can calculate that if you have the time. So let's use, for instance, aluminium and say that. So you'll use the aluminium in the equation I'm giving, the value I've given you there for aluminium. Say that determine the resistance of aluminium wire the resistance of aluminum wire of length 120 centimeters and diameter 0.2 centimeters. So you can try out that. Determine the resistance of aluminum wire of length 120 centimeters and diameter 0.2 centimeters. Assuming that the wire is cylindrical. So I'm waiting for your responses. The value of resistivity of aluminum is 2.8. The resistivity of aluminum is 2.8 times 10 raised to negative 8 ohm meter. So what is the answer for those who have done it?
$0.1070 ohms.
0.1070
ohms.
Okay.
Oh, sorry, 0.01070. Sorry.
0.01
070 ohms.
070 ohm. Okay, that is an answer from one of you. Any other?
0.010694.
0.010694. Okay.
Yes.
Any other?
0.010694.
The same.
Yes.
Yes.
Right. For identical responses, there's no need again of mentioning, unless it is a unique one. All right, so I think if you are to solve it, maybe this may be the correct answer. If most of you are getting that. And let's try. Let's go through it quickly. Maybe for us, those of us who may be stranded and how to go about it. Now, we know that R is given us L over A. That is the formula that we have. So resistivity is already given as 10 raised to -8. Then we also have L as 1.2. The conductivity so that we also have to get that. And the diameter, that particular wire, thickness, 0.2.
Can't hear you clearly. We can't hear.
Now, those who are busy here, let me get them.
Alliance High School.
Oh.
Admit.
Okay.
Alliance High School.
No, that one must be a small error, and I cannot mute.
Alliance High School.
It's okay, Brown. It's now fine. Okay, we are almost done. Oh, our time has really gone. I'm just realizing that. So R will be the 2.8 and 10 -8. So L is 1.2. Then here. So I hope you did the correct computation that is required. Pi is just pi times R, which will be 0.001, then you square that. So I expect if you do that correctly, you will get the same value there as 0.01069, or for those who want to round off, ohms, like that. So that is what we have there. So you can practice more on that. And maybe before we call it a day, Now we have the idea of resistors and resistor networks. We have no option but to begin from there next time because it's a very critical area. Is that okay?
Yes.
Yes.
Yeah.
Yes,
So for now,
yes.
for now you can
Next.
do practice on those areas.
Yes, practice.
Okay.
Yes,
Okay.
you practice and you understand.
Alliance High
Don't
School.
you get me? Don't cram things. Make sure you understand the concept. No cramming.
Yes.
Do you agree?
Yes.
Okay,
Yes.
so fine.
Yes.
Then you can enjoy the rest of your day. You can prepare for the next whatever you have next.
Yes. Alliance High School.
Thank you very much.
High school.
Thank you.
Alliance High School.
Alliance High School.
Alliance High School.